Good morning. We are going to talk about network on chip security. So, the first half will only talk about the security and design for security solutions, and in the second half we will talk about how do we use machine learning to basically kind of mount attack on some of those security primitives or kind of detect some of the security vulnerabilities. So, it is a lot of techniques I am going to talk about, there are many more, but the key idea is if you recall our earlier discussion, whenever we talk about security, first question we ask, if we already know there are so many vulnerabilities, why did not they design certain mechanisms so that these security attacks will not happen. So, that is why the first part of the talk I am going to talk about what are the designs out there or researchers have done that is designed to make it secure, right. So, think about the words encryption, authentication and all that stuff. In the context of network on chip, there will be few more I will introduce. But before I begin there, any devices you look at, whether the form factor is small or form factor is big, whether it is a car, airplane, your phone, gadgets, the core brain inside is a system on chip. Even in your phone there is at least one system on chip, there could be many. And when you open that system on chip and zoom inside and pull it up, what you are going to see conceptually something like this. Of course, they are not placed at the boundary, just for picturization I am showing. So, you are going to have memory, processor, DAC, digital to analog converter, analog to digital converter, FPGA, controllers, graphics processing unit, and it is not just one of each. In the next slide I will show you even the processor, there could be hundreds of processors inside that single chip. So, today's talk is about how do these people talk to each other. What is this communication fabric? Before you understand this, you have to understand how is all these computers talking to each other. How is the cell phones connecting to the tower? That is a network. The cell phone talking to the cell phone tower. When you call your let us say your friend in Switzerland, then it talks to whatever nearby cell phone tower. From that tower it might go to the satellite, from that satellite it might go to the satellite in the Switzerland side, that goes to a cell phone tower, then that the signals go to the cell phone and that receives it. That is a network. You may not see it, it may not feel like, or you can think of bunch of computers that is connected here to the IIT Guwahati network. It might be kind of normal copper wires or it could be optical fiber. Those are the physical wires somewhere, optical fiber or copper wires laid down in these buildings. For example, right there you can see this all these cords going in. This is a network. Some of them are local area network like the things you see in this room. Some of them are global area network like the network that is all these departments, computer and all this connected, and people might make a hotspot with Wi-Fi, just all of your devices connected, that is also a network. And this Wi-Fi hotspot network might connect to this network, might connect to wireless network, but they have to somehow connect in some manner. Same analogy we are applying in a restrictive environment. So, before I go any further, the first question I want to ask, that is the question I asked, right question I asked about 10-15 years ago to myself. There are all these solutions already exist in the local area network, global area network, wireless network community. Why should I do research on this area? Why can't I just take those solutions and implement it here? I want to hear your thoughts. Why can't I just take those solutions and put it in here? Or if I am in the company, I already know the solution, how encryption works, how authentication works, I exactly know the primitives, cryptographic libraries, I know everything, I just implement it. What is the problem? Even before that I will ask the question, why did I do research in that area in the first place? There is nothing new to be done, everything is understood, well known, why would you do it? That question I will answer, because the network on chip even today, even after 10 years of research, it does not implement any security primitives here, most companies do not. The assumption is, remember what is the assumption of thread model? Assumption is these communications are not assumed, are assumed to be trustworthy. In fact, I forgot to mention in the trusted execution environment definition, when they talk about, let me just draw two cores here. let me just draw two of them. Let us say this is core 1, this is core 2, and then these two core are talking to some folks here and there. This idea of this core 2 talking through this path in trusted execution environment definition, that is not even assumed to be a problem. Problem is the application talking to each other, are they accessing the pages right. So, when memory is involved, antenna is getting on, memory, page, somebody accessing my location, but this traffic C1, this might be in the enclave, this traffic going through it, somebody else's traffic going through this path during this bus communication. I will show what that exact communication is. The assumption is if bunch of zeros and ones are flowing through this way, bunch of zeros and ones are flowing through this way, they do not have any computing ability, they are like water flowing through, or whatever may be the assumption, there is no attack surface. So, even trusted execution, if you open it up, that document does not even talk about this as a potential vulnerability. So, those things were not implemented, and that bothered me. I started. Now, I ask the next question, even if you start research, it is the solutions exist. We exactly know two parties wants to talk, just encrypt the message and done. What is the difference in layman terms? Yes.
So, probably because the conventional protocols that we have a higher overhead, and that kind of overhead we can't take on a SOC.
Absolutely. You should guess 20 out of 20 or 50 out of 50 in that exam. The idea is those have no resource constraint. Let us say your computer talking to another computer, those are connected to the power supply or battery, whatever it is. It can take computational complexity, amount of battery power or power it takes, it does not matter. Probably it does, even there people are trying to come up with. But here it is a resource constraint, lot of resources, it is not necessarily just power. Even the point to point communication, whether it should happen in 2 millisecond, 2 nanosecond, there is a tight bound, but there is an advantage. This is not like in normal domain, the network should work even if like right now there are 16, 20 people here. If there are 200 people here, network still should work. So, you kind of design it like 200 people can connect computer, 500 can connect. Here you kind of know, it is still in the order of 100. In an automotive SoC typically have about 200 to 300 components, but it is not like thousands or millions. It is not like in the cloud nobody knows how many computers are connected and you need to deal with their communication. So, we do not have that story. So, it is kind of a application specific. So, you can take that advantage, customize for it, but that is also become a disadvantage because it is a resource constraint. You do not have unlimited time to compute that highly accurate, really security robust solution. So, that is why I took a deep look, should we have any solution at all or we just let it go the way it is. So, I am going to just talk about those issues, but before I go there, I promised that I will show you that the number of cores or even the processor core. Remember, it has lot of component, even any of the component you look at, they are also in the order of hundreds, whether 128. So, right now we have 128 around 180 cores, whatever it is, there are those many processors. Now, every SoC may not have those many cores, some may have 4, 8, some may have more, but you need to talk about connectivity. In the past 20 years ago, bus used to be de facto solution. In fact, when I talked about security engine, bus is used as the solution. When you are putting 5, 10, maybe 16 components, it would be fine. In fact, there were cases where many designs would have everybody to everybody connection. So, which used to be fine in 20 years. But later it becomes a problem when you are putting so many components on the same bus. If you are putting let us say 16 of them, then 16 even if they are sending 32 bit data per clock cycle, 16 multiplied by 32, your bus size has to be that big, or they need to do time multiplex or bus arbitration logic. Either way, that is not a scalable solution. You cannot go 16, maybe you can still accommodate 32, 64, 128, it is not going to work, everybody will slow down. So, then this is also not a solution, you put just somebody and try to do from many reasons. So, the cost, remember inside the chip there is no soccer field there. So, that free space you can just draw whatever you want to draw, it is all restricted, and any line trying to cross any line, parasite effect and all that, plus the cost of area, communication overhead. So, it is not even feasible when number of nodes are really large. So, then there are a lot of solutions came in, but this one I already showed you. So, the supply chain vulnerability would equally affect, earlier we talked about affecting cryptographic module, affecting computing nodes, even the network on chip is also an IP, that also will affect. So, the bottom line is, if you look at any system on chip, it would, or any device for that matter, it would have some computing nodes, some for storage, which is think of processor, think of memory, and some for communication. In today's discussion, we are going to focus on communication, and there is a lot of research on securing computation, securing storage and computation from different abstraction level, right. You can design secure hardware or cryptographic module, you can do secure compilation like Dr. Karfa does, you can do secure synthesis, all of those focus on computation. You can do secure storage devices and non-volatile and all that, there is a lot of technology at different layers. So, communication, there has been very little work on the SOC space when I started, now there is a lot of work. And another reason, the motivation factor for me was when I started thinking, if an attacker can get access to that communication, which is hard by the way, it is not that easy, you just get into somebody else's chip in the communication you can observe, but if you can, everybody is talking through that communication fabric. Even if it is encrypted, you can still figure out something. Let me ask this question before I go further. So, if let us talk about just processor and memory, let us not complicate it. Processor and memory talking, right, and it is all encrypted data, all encrypted data. My hypothesis is somebody sitting here can still mount an attack if they can observe this bus. Can any of you tell me what attack can I do? It is all encrypted data, and assumption is you will not be able to find the key, you do not know the key. Good encryption, no side channel, nothing. What attack can I do?
Man in the middle or eavesdropping.
Eavesdropping, so what signals are going through, I am talking to Dr. Karfa on the phone, you eavesdrop on those signals, it is all encrypted signal, you do not know what we are talking unless you are listening right there. So, eavesdropping is not going to help here. What kind of attack you can do where you can find something out of it? Actually, you can do lot of type of attack. Let me tell you the simplest one. So, for example, by observing this I can figure out what application you are running with little knowledge. I know you are running a sorting algorithm, all I have to figure out, is it bubble sort, is it for example insertion sort, and each of those bubble sort will have 2 for loop, insertion something, all I need to figure out that loop, but how do I figure out from the encrypted data? Remember, the data is encrypted, address is not. Data is encrypted, address is not. That is why I exactly know where processor is requesting, and when what the data coming back after load, that I do not know, that is encrypted, but the address is going to is not encrypted. And in fact, you will see this problem even in network on chip, that the header is not encrypted, because if you encrypt the header, the problem is whoever is receiving and trying to figure out whom to send, they need to decrypt and figure out, that is going to slow down everything. Header is not encrypted, it is just the message is encrypted. So, your email you want to send is broken down into pieces called fleets. Every fleet will have header bit, this bit, control bit, authentication bit, the message authentication identifier, all that. So, data is encrypted, but the header part, minimal part, that is not encrypted. Either way, once you know that, then you are basically seeing that access to a location is 10 times, then followed by something, then followed by something, and this story, these addresses are repeating 20 times, and then there are 2 loops of some addresses, you would be able to construct the structure, and from that structure you will be able to figure out whether it is insertion sort or bubble sort. There are many mitigations for that, but I simply wanted to say, when your brain is saying, well, I know it is encryption, therefore it is all safe, think again whether any other type of attack you can do. Again, if you did not know whether it is a sorting algorithm, you did not know anything about anything, for you to figure, even you might have got some structure, but are you going to take that structure and try to figure out all the algorithms in the world that is available and whether it matches with anybody else? That is not going to be feasible, right. So, that is why security attacks are always in steps. You know a little bit, you talk to somebody, get little bit information, then use that to talk to somebody else, and then you mount the attack. Any questions on this? So, the key idea is when I started is if somebody have access to the network, they pretty much get all the information. So, it works both ways. If I can implement a security primitive in the network, I can protect lot of stuff, I have a better visibility if I am a defender. If I am an attacker, I have a undue advantage, it is a focal point. So, now this security story is challenging compared to actually even normal network, because first of all this is a source, this is a destination, they want to talk, I still did not say how they are connected, but no matter how they are connected, at least in our research we considered 3 technology, there are few more, so that you know, but 3 major one, and this one most of you are aware of, electrical. The wiring, that the wiring all you have, you send high or low or 5 volt or 0 volt or stuff like that, twisted wire, and I do not want to get to the details of discussion, but electrical wire communicates all that information once you make the packet, then all that stuff. But what you might not be aware of is, this also you might be aware of, because most of the networks these days you know or you do not know, even below the ocean, those are all optical fiber network. It is based on lights, lights are traveling. So, you convert the data into light, and from that light again you convert back data. So, they have a lot of serious advantages, and some of the attacks on optical fiber is basically you try to bend, you shake the ground in some way, and you can do some distortion, but it is much more robust than electrical. Think of a glass tube, literally you are throwing light through it, that is how it is, but whatever it is, that is the optical NoC. It is not very popular. Are there SoC prototypes? Yes, but it is not as prevalent as there for the network on chip. But in real world, actually there are more optical networks, or if you look at total amount of data traveling in the world, most of them are traveling through optical network as of today. When you are getting all these high speed internet, Wi-Fi at home, it is only possible because of optical network. So, optical network is kind of very common in the classical computer communication network, but it is very rare as of today in the network on chip. And then there is a in between, which is wireless, of course, is pretty much everything is wireless in classical computer network story, right. And it is somewhere in the middle, there is not too many prototypes, most of the computers and things you buy, those are in electrical NoC, but there are wireless NoC, where the idea is you have all these components, I have details later, and you have, earlier I used to call them micro antennas, now they are nano antennas, nano dimensions of antennas, but it has exact same property. Next to your house, if you have seen all these big tower, those are radio frequency communication. These components understand and receive, think of each of them is a cell phone, think of it. They understand those communication, and you still have to deal with all these problems, the interference, right. To understand that, think about there is a tower here and then there is a big gathering, 100,000, 200,000 people in a field, maybe convocation day, that day talking would be really problematic, not because everybody making noise, because it is tower and congestion, RF. But if there is a tower, 100,000 people sparsed around the thing, it is not a problem. Here tiny place, all these antenna, and that kind of story is a problem. Nonetheless, the point I wanted to get across, there are a lot of ways these people can communicate, and most of the solution today, even the wireless one, they are hybrid. That means everybody does not have wireless communication capability. So, they have, there is a electrical as well as there is wireless, and I will show you that hybrid topology, where, or let me just draw one of them just to get an idea. Let us say it is a 4x4, 16 components connected in a mesh, and let us say this one has a tower, and maybe just for fun this one has tower, it does not make sense. So, then if this is source and this one is destination, the electrical would have been, let me use the red color, electrical could have been this way, or it can come like this to this wireless tower, this wireless to this wireless it comes, and then from here to here electrical. Now, in this one it seems like direct electrical would have been just good enough. Why do I go to the little electrical? So, this is similar to, this is your highway. Before you get to your highway, You do little bit of local city kind of drive, then you go to the highway and then you get out of the highway. So, that kind of hybrid model also exists, and that is all the most of the prototypes that exist in the wireless, they are of this kind, and there are not too many of them. Any questions? Yes, please.
So what are the advantages of going wireless or optical?
So, actually the optical or wireless has this problem of you need to wire them. You need to wire them, that connectivity, that wiring, that space, all of that problem is gone in wireless, that is one. Then there is a second advantage. Electrical would be electrical wireless is same multi hop. So, you want to go to S to D, it is 1 hop, 2 hop, 3 hop, 4 hop, 5 hop. You have to go via some other people, right. In this hybrid, of course, you still have 1, 2, 3, 4, but in general if everybody has a communication, it is a single hop communication. Even in your cell phone, I do not think it is a single hop for anybody, right. When two of the people are talking, it still go to the at least a tower, at least 2 hop, but nonetheless that is the key idea. You reduce the number of hop, but it introduces its disadvantages, all these RF interference and all that stuff. Any other questions? That is a very good question, right. Now, there are lot of there are many other things to deal with when you want to talk about network on chip security, which is like any other design principle, you have this eternal trade off. Do I be honest? Do I make lot more money? No, I am joking. So, you have earlier you had performance, energy and area trade off, now you also have a security one, and by the way this story is also true for classical computer networks. If you want to implement a very secure algorithm, it is going to take a lot of energy, it is going to slow down your performance little bit. Like a typical AES, even the smallest counter mode, it would take somewhere around 32 cycles. So, earlier you are executing one instruction every clock cycle, now you have encryption, you have to wait for 32 cycle. Whoever want to use the result of that has to wait for 32 cycles. Load instruction, we already have a problem, cache may be miss or hit, now cache controller is encrypting it, even if it is a cache hit, it is going to take 32 plus 1 cycle, 33 cycles. So, every cache hit it is 33 cycles, that is too much of performance penalty. Do I want it to be secure to avoid somebody eavesdropping, or do I want to be fast? Then there is a middle ground which I will talk about, which I do not want the highest level of security, I will settle for little lower, but I do not want to want to do anything kind of story. I want to do something, but I will not go that far. Any other questions? So, if you think about it and look at it, today there are many solutions, and today I am going to talk about mostly a solution that is mesh based, but there are many more and each has its own research challenges. So, in mesh based solution, the key idea is you have lot of components and they are, so for example, this one 4 cross 4, there are 16 components, think of 16 processor cores, they are connected exactly this way. If source want to talk to destination, then it goes through each of the nodes. Even cell phone world, there was this idea of peer to peer communication. So, instead of if two of you are talking either to yourself or somebody, should it go multiple people talking, should it go to the tower and come back, or should your phone use the another phone nearby its range or Wi-Fi range and actually travel through that. Now, you might think that model is actually popular in many countries, peer to peer communication, and the way it is kind of a reward system. Why would I use your phone call to be routed through my phone? The way I use, then the company gives you data, gives you your free whatever monthly subscription, it becomes free or half. So, then there is some understanding of that nature, but whatever it is, here it is basically peer to peer. For this information need to route, it need to go through other nodes in the network. Remember, those folks are also talking to other people. So, we will zoom in to see how all these happens. But before I go any further, when I try to do network on chip secure, we are still addressing exactly same problems we addressed in any other network, which is authentication, who is talking to me, We are talking about data integrity. Did anybody modify the data when the communication going on? Did anybody I do not want anybody to know what I am talking. And let me start with the first one, anonymous routing. So, what does the word anonymous means to you? Anonymous basically means if I am talking to somebody, it is okay, you understand I am talking. I do not want you to know whom am I talking to. I do not want you to know who is my girlfriend and boyfriend. I do not want you to know. It is okay, you know I have somebody, so that I can boost my chest, it is okay. But the question then attack is, how do I break that anonymity? How do I figure out whom you are talking to? Are you talking to my girlfriend? Then I have a serious problem, right. I need to know and break that, right. Most friend circle, that is how they break this whole not understanding the line, that there is a line between even friends. So, this is a source and destination talking, in between there is a node, malicious node who is listening. Now, this is where the threat model starts. This is where supply chain vulnerability comes into picture. If you do not believe this threat model is possible, then you should not pursue this line of research, which is one of the node. In fact, it is not the node that is malicious. Remember, each of the node I zoomed in, it has 3 parts. One part is the IP itself, let us say this is the processor, this is the CPU. In addition to that, you have the shared resources and the router. The shared resources typically is network, for example, it is the network interface card. Think of glue logic, whichever way you feel comfortable. So, this was the network interface and this is the router. Router is the one who maintains who is talking to whom. Remember, this processor is computing whatever program it is supposed to compute, but the router and remember, this router, if there is information coming for this processor, this router will forward to itself. So, a better picture would be, think of, I have few other pictures. So, think of this as a network interface and router, and then there is a IP, the CPU is hanging from here, that would be a better picture. Everybody has the computing core and network interface and router. Router, think of, for the time being, think of a lookup table. A request comes in, a address comes in, you try to figure out where does it go, and if it is a XY protocol, then you go in X direction as much as possible, then you go in Y direction, but that algorithm is orthogonal. Any questions on this structure? So, the threat model is there is somebody in the middle sitting and trying to understand who is talking to whom. So, the objective of this one and what we will try to present, how do I stop that, they are figuring it out. So, basically they are tracing packet, they are doing different kind of analysis to figure out who is talking to whom. Now, before I introduce, you guys have no allergy on onions or garlic, right. So, I am going to introduce the solutions that exist in computer networks community, and it is called onion routing. I did not invent it. So, onion routing, basically idea is same. Let me go back to the previous slide and show you what onion routing looks like here. So, the way onion routing works, let us say, let us choose the same one, source wants to talk to destination, and there are multiple people, let us give them name. A is already given. So, let us call it B, C, E, these are the nodes. For S to send a message to D, here is the message, see how onion forms. First of all, the message need to be encrypted with the key of whom? Ideal situation it should be D, but in a onion routing the lowest layer is always the key for D. Then you add another layer that was for key for E, with key of E, public key of E. Then another layer, I think very quickly I will go out of space, then key of C, then I am just drawing this part, then key of A, then key of B, that is the onion I form. So, you are encrypting this message with the key of D, that is exactly normally we do. Whoever you are sending, take their public key, encrypt it. In the onion routing, which path is traveling, if you know the XY routing, you exactly know which path it travels, then you know who are the components it is going to go through, and everybody has access to everybody else's public key, and you basically encrypt that message with those public keys, right. And then you send this one to the B. Can anybody help me, when it goes to B, what happens? B decrypts it using its own private key, and that would result in this layer would be gone. It will be able to open only the outermost layer of the onion. Then that one goes to A. A is malicious in this case, but all A has the ability to open it. A does not know what is the message, because this layer A cannot open unless it has the unless it is able to compromise C and found the private key of C, right. So, that happens, and then it goes to C, C opens this layer, then it goes to E, E opens this layer, then it goes to D, D is the only one who can open this layer and then know the message of M. This has huge overhead. You have to do so many encryption, packet and message becomes larger, although pictorially I drawn it, in reality it is still bunch of bits, right, even after encryption. The good part of encryption is the size does not change, unlike compression, size reduces or decompress you become. In compression, size remains same. Anybody knows what happens to the compressed data? One dictionary word? It become randomized. If it is a perfect encryption technique, it become perfectly set of random bits. If you can compute the entropy and figure out this perfectly random set of bits. If it is not a good encryption algorithm, because when things are random, applying any form of attack, any kind of thing does not work. That is the key idea, but either way. So, is the idea clear what is anonymous routing and why onion routing would be really expensive? Okay. Now that, so for the first attack and solution I am taking little extra time, but subsequent one will go faster, because then all we talk about the solution, not all these details how they travel, right. Any question on this one? Now, anybody, so onion routing we talked about, like layer after layer. Anybody knows what is the garlic routing then? What is the difference between onion and garlic? Nobody knows? Onion has this, yes, go ahead please. Onion has the story of layer after layer after layer. Garlic also has layer, but in addition to this layer, let me use a different color, so it would be interesting. It has this, what is it called, cloves. This has all these cloves, they have their own layer, but the interesting part is, let me try one more. They have their layer, in addition there would be some outer layer. In addition there would be some outer layer. So, that is basically the garlic. Can anybody then connect how garlic communication will happen in my previous example? Onion I said you just encrypt for each of the people in the route, and how would garlic communication will happen? Yes and no. So, this one garlic communication, assume you are not sending for one party, you are sending for multiple parties, and where it happens, if you took computer architecture course, like when you have invalidation messages. If a cache is trying to write in a multi-core scenario, cache is trying to write into its cache and other people may have a copy of that data in their local cache, you send invalidation messages. So, there are many such scenario, you send the same message to a lot of people, then you can do this. Even if you are sending different messages, let me create a scenario. Let us say here are the kind of nodes. So, let us say this one is trying to, let me use a different color. This one is trying to talk to this one, and then this one is trying to talk to this one, and all that stuff. Then you can see, at least for certain part of the story, we could create garlic. So, this message is for the clove, one of the clove, this message is for another clove, and that actually have a higher security strength. And but there are many, invalidation is one perfect example. Any kind of multicast communication, instead of treating every request as a independent, because if lot of people are trying to go to, let us say from here to the airport, and from different halls they are coming with their cycle or whatever they can come, but somewhere there is a bus pickup place that will go to the airport. So, at least that part of the journey they are together, that is the idea of garlic. and right. So, basically it does not, it is coming from multiple sources, then you form the garlic propagates, again it can go to different destination. Now, all of the solutions actually existed in traditional computer networks. We borrowed those ideas and make them lightweight, that is basically the key idea, and the details are not important, and this is for understanding that you have to read that 2-page or 3-page paper of Sameer's secret sharing, how you can use a Lagrange basically coefficients in a polynomial, and this is for the first time I realized why they taught Lagrange and all these Laplace. Laplace at least I understood, because when you do electrical whatever circuits design and all that, you have 1 over S and all that. Lagrange I never used, and I always wondered why in engineering mathematics they teach these things, nobody will ever use. And this is the first time I used. 40 years later I realized, oh, that is why they teach them. But anyway, so the idea is very interesting. So, if you take points on the curve, and that is how our solution actually work. If you take points on that Lagrange polynomial, and unless the attacker, whoever that the malicious person is, it can compromise all the nodes in the path, it will not be able to figure out the message. Onion routing explicitly do this. Think of conceptually each point is an encryption, but here it is literally a point. Remember elliptic curve cryptography, it is a point on the curve, it is literally a point on the curve, it is actually not you are doing encryption of the whole message. It literally you choose points from that curve and use those points, somehow encode it in the message, put that in the message, not explicitly encoding, that will work. So, anyway, so then basically that is how it works, and if you want to see the math how actually it works, we have the full math, but I am not going to go through all these math how exactly this may look complicated, but it is basically saying which is one time pad, what is the message, how you OR it, how many bits of it, it is the exact details how it is. And let me see if the animation work. So, if S is trying to talk to D, it is basically, oh, this circle should have been here. It basically it is going to the router of the next one, and then that router basically trying to check, and then so on and so forth. So, the key idea is everybody knows only the previous where it is coming from and where it is going to next, that is the catch. One point in the polynomial only it knows who is my predecessor, who is my successor, it does not know anything else, it does not know. So, unless so you can still anonymous you can break if this one knows where it is coming, where it is, unless this is the source, this is the destination, then by default it is broken. But if the predecessor and successor are not the source and destination, you can never figure out based on this formulation, because there is no option for you to ask, can you tell me who was the predecessor, where it came from, you cannot ask that question in Lagrange polynomial. So, that is basically the one. So, nobody knows where else it is, and just I am showing some results quickly. So, basically anytime you do network on chip research, first thing you have, or any architecture research for that matter, these days GEM5 is kind of the de facto simulator you use. Most security attacks people do not like results from GEM5 simulator, people want you to do on the actual computer. Now, it is possible. Earlier dumping data from the NoC was not even possible. There is no way you can dump data from a NoC that is on your computer. Now, some of the latest servers, there is the ability, if you might be able to do that. First of all, that processor should have NoC enabled, network on chip, right, and some of the latest processor and server grade processor, they have the NoC and the ability for you to download. But all these years, early days, there was a processor called simple scaler, people used to do work in those, but now it is a processor of GEM5. Think of this is the computer architecture simulator, this comes with hook to many other softwares and simulators, and that allows you to kind of simulate the mesh, whatever network you can choose, you can run synthetic benchmark, you can run real benchmark. So, basically if you have, let us say you are modeling a 2 by 2 core, you can tell on this core I want to run a bubble sort, on this one while an insertion sort, this and that. So, then real traffic will flow, then you do not force, oh this is my source, this is my destination, whoever is talking to whom, wherever now question is, if bubble sort is running here, insertion sorting running here, why would they talk to each other? Any thoughts? Why on earth, if a processor is running a program, why would it talk to another processor who is running another program, totally different program? Why would they do that? Sorry? Working with same data typically will work, but that your argument will work when you are kind of parallelized a program, you parallelized into thread. Let us say you are adding 100 numbers, you divided 50 getting added here, 50 getting added here, that still do not talk, but one of them or both of them has to send it to somebody, maybe this one sends, then you add the last two numbers here, there is a talking. Most of the other time talking is one of them is running program, but the one I did not talk about, they also need to have a node where the memory is sitting, memory, cache and all these modules are sitting. Now, I am not talking about the local cache, the shared cache, main memory. So, everybody while they talking, they need to go to main memory. In fact, later you will see the denial of service attack is somebody is going to spam lot of requests to this memory, knowing memory is the bottleneck, let us just overload it, so that when legitimate load store request goes in, it cannot get served. There are many scenarios while people talk, either it is a multiple threads of the same program, then natural data sharing as you said, or how that the memory is placed. And remember, memory may not be placed in one place, this could be implementing a distributed multi-core architecture, where memory is also divided into multiple pieces. Then they have distributed directory, distributed memory and different pieces of memory. Typically memories are connected in the outer layer of the node for obvious reason, but whoever it is, people or a node will talk to another node for legitimate reasons, right. So, therefore, the two things that is important. So, one thing is most people spend 3 to 6 months learning the GEM5 simulator itself, GEM5 how it hooks to different kind of routing protocol and all that stuff. Then the next thing they do, two things are important in research, is the average packet latency. Of course, who is talking to whom, that would determine the delay, right. But the average packet latency, say everybody is talking to everybody in that scenario, what is a time you send a request, on an average how much time it takes for it to reach there. Remember, there are a lot of things I am not going to talk about, which is what protocol is it XY protocol and all that, number one. Number two, if a packet does not get delivered for whatever reason, there would be a the reminder come in, that would be a message, and would it retry after 10 millisecond if the acknowledgement does not come in. There are in the protocol itself all these embedded. I am not just talking about it. The way I am talking, as if you just take a packet, message, packetize it, send it, other party will get it for sure, but in reality that does not happen. Even if you packetize it, because of some congestion aware routing, they may go through different paths. Some of the packets may reach on email divided into, let us say, hundreds of packets. Some of the packets will reach, the remaining packet may not reach. So, it has to be resent, then in the destination it will be composed, then you see the email, all this stuff happens. That is why when you are spamming email, just think about it, think about, humanize these networks and computers and think about, I do not want to give this much of pain to that person, just do not do that. Like when you forwarding all this spam stuff from your social thing, just think about these computing nodes, what they are doing, packetting, dividing, header, encryption, onion, garlic, spices, curry, rice, have some respect for them. Okay. So, one is the average packet latency, second thing is execution time. Here I am showing normalized execution time, whoever is worst call it 1, and but we can plot. So, what is the execution time end to end and how long does it take? Typically this is supposed to reflect on this. If average packet latency is improved, your execution time is supposed to improve, but those are the stuff. But anyway, I am just going to show some results. So, this is no anonymous routing, basically normal computation, which is the NoCs today. And then we have the anonymous routing. If you use the existing garlic or onion, it is going to take a significant amount of delay would be too bad, execution time would be too high. In contrast, if you use the Lagrange polynomial based hour implementation, then it is going to be really small. And in terms of improvement, let me see, I have number. Let me delete some of the space here. So, basically the overhead of our implementation is about 18%. If that is acceptable, that is good, but if we use the existing, it is going to have about 70% overhead. In the execution time, a similar reflection. So, I am going to talk about one more idea before the break. Any question on anonymous routing? And the next one I will just focus on just that work, we will not get into the details of this. Yes, please.
Based on the architecture, the grid based P2P communication which was shown, sir, like in the conventional we have various methods to overcome collisions, CSMACD and all. In this, how are we mitigating collisions?
So, first of all, when we discuss in the network community, there is a common understanding. When you are talking in application layer, do not ask question on physical layer and network layer and all that. So, in this particular scenario, it also has very simplified bus contention mechanism. This router, and each of the router has the story of how many requests came in and who have the priority, whom should I forward first. Everybody is getting so many messages from so many places, which one should I route, do they have a priority. So, there is a miniature, all that stuff you said, there is a miniaturized version of everything implemented as of today in the real NoC devices. It is actually implemented. So, when we work, we do not worry about it, we do not talk about it. The next one I am going to talk about is the incremental encryption. And so, the idea is when the two people S and D wants to talk, so packet get encrypted and then the encrypted data goes through and packet get decrypted. And remember, so each of the module that is there, it has a router, network interface and actual component itself. It could be processor, it could be memory. Here a processor is sending a data or processor is requesting a data, right. So, in this story, if there is some man in the middle, man or woman in the middle, they will not be successful, because in the communication it is a encrypted data. But the problem is the overhead is too much. If you want to implement traditional encryption, we talked about all these stuff, AES, counter, Galois mode, then we talked about elliptic curve cryptography and so much. So, RSA, it would be too expensive to implement. The delay would be too much, execution time would be too much. It is unacceptable, right, because you are sending a load request. Earlier, what did you think? We send a load request, it is in cache, it takes one cycle. Dr. Karfa asked, why does it take more than that, right? Because of all these stuff goes on, then your delay becomes much higher. Because in simplified model, we assume wherever the processor is, cache is the local cache is connected, but any other cache, any other memory, shared cache, it is just all over the place, right. And then what is our insight on this? The insight is, if you look at the NoC traffic, by the way, this insight actually true even if you take the benchmark spec benchmarks on the processor, all these 32-bit data you look at, most of the bytes are zeros. It is not just in the network traffic. And the interesting part is the email you write, the email I write are different, but at the packet level it turned out, when you look at the typically packet sizes are 64 bit, 64, 128, whichever you want to implement, and when you look at the data, whether there is a 64 bit data, so that like 8 bytes 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8 bytes, it turned out that most of the bytes are 0. Actually, if it is 0 or not, it is not important for incremental encryption. 80% of them actually have only one block that has data, other data is similar. In this context, who is similar and who is different compared to the previous one. For incremental encryption, that is what we observed, that 80% of the packets have only one byte. In fact, in most of the cases it is not even one byte, only few bits different, but we still look at byte level. Can any of you give me an idea why? Why you have all these data and we have 64 bit all these packets and only few bits are different compared to previous one and the next one? Where this should happen? Because it is not like 1 or 2, it is 80% of them. There has to be something obvious here we are missing. What is it? Yes, please.
The data would be less and header and padding would be more. That's why.
But header and padding, remember, it is going to different places. So, they are all supposed to be different. Why would it be similar? Remember, I am saying only one block is, it is not importantly significant, only one block is different. The previous block or data that was sent, previous packet, and this packet, only one block is different. Why? Where in your programming paradigm you have seen something that justifies this? You are still thinking. When you have a load instruction, think about processor and memory talking. If you have a load instruction, load to R1, right, and if you have a for loop, of course, that is not how we write a program, we have only one load and repeat. Load to R1, then you have an address, this address increases by a byte number, that is it. Of course, this is a silly example I mentioned, probably the next load instruction is load R2. Technically speaking, even if this address is for one, at least 2 bytes should be different, this byte or that byte should be different, but nonetheless that is the key idea, that is the key idea, that the load, the binary for load is exactly the same, everything else is exactly the same, only thing changes is the destination register and kind of the address. And even if the address, if it is in a loop or you are going for an array, you are going for the first address, then the +4, then the +4. So, it is just changing by a byte. So, it should not be a surprise that only one block is different compared to the previous one, right. So, in fact, as I said, this observation is true even in general purpose computing. Even if you take spec benchmarks, do all these analysis, and I forgot to tell you, in architecture community, when you write paper compared to other community, you have to do lot of analysis, you have to set lot of context to show why that is relevant, who gets benefited and what is the observation. So, if you do that analysis, you will observe about 40% of the cases everybody is 0 except the least significant byte, everything is 0, that is how its computation happens. And anyway, so when you sum it up, 80% of them have one block, 20% of the things have 2 blocks difference. So, although you have like 16 bit blocks, so there are actually 4 blocks, this is how the difference is. So, the 2 of the blocks are always the same kind of story. So, then how does this story then works? Let me just finish this. So, basically in a traditional encryption, if you are instead of 16 bit block, I just made it a small 8 bit blocks just for the illustration, or you can think of 16 bit blocks. So, if traditional encryption, you just encrypt both blocks, right, and then another set of blocks came in, you encrypt those blocks, and let us assume this case instead of 32 cycle, it is for 20 cycle it takes for encryption, and then you keep on doing for this series we need 16 clock cycle. If you want to do incremental encryption, and so by the way, I did not invent incremental encryption, there are technologies I did not talk when the cryptographic discussion I did, like Hummingbird and variations, they actually support this incremental encryption. Lightweight solution is Hummingbird. And so then you do 20 cycle, but the next time when you are looking at these data, we are observing that this particular block which I put in there just so that you can see they are actually same, right. So, they are actually same. So, I do not need to do compression on this one, I can just do compression on this one, that is basically the key idea. So, these 2 are same, so I do not need to do anything, but of course, these 2 are different. Now, if I put this data, that is why it is in purple color, we kind of see these 2 are same and those 2 are different. So, because the same one I do not have to encrypt anymore, I only encrypt, but I still have to pass some extra few bits to convey that which one I compressed, which blocks I did not compress. So, that it takes the compressed data from there, and details again you can see that is the basic idea. You save on that, and even if this one instead of taking 20, if it is kind of take your 22 cycle, because you have little bit of extra manipulation. So, then total is 42 instead of total being 60 cycles. That is the key idea of incremental encryption. and rest of the stuff I am basically going to skip. So, basically in the experimental setup it is a mesh NoC with different number of core, and as I said in networking community or network on chip community, two types of benchmarks are expected you show. One is synthetic benchmark, where you kind of randomly generate traffic with different injection rate and how quickly they kind of sending data. One is real benchmark you run on those cores, and then you show the result. So, basically in terms of network on chip delay, the compared to traditional encryption we can produce 57% improvement. In case of here it is about 10% improvement. So, we stop here, we will start at 11:30. Thank you.